Okay, one part that we have at Oklahoma State that we're very proud of is our senior design projects. And our senior design is interdisciplinary, where we include people like, electrical engineers, engineering technologies, computer engineers, electrical engineers, chemical engineers on occasion, but between them they can do some very remarkable projects. So today is the day that throughout the whole semester that the students are able to show off their projects and compete for things like Best in Show and the Best Senior Design Project or the Most Innovative Senior Design Project. It's actually a lot of fun. Hello, I'm Ed Rowland. I've been there multiple times in Puebla, but here we're going through all the design projects that we've done at Oklahoma State for our senior design. And here we have autonomous foosball, where we're actually training AI to play against humans in foosball. And it's better describe this and who built than somebody who actually built it. And I'm sorry I don't know your name. Please introduce yourself and talk about your system.
Hello everyone, my name is Cosette Dyer. I am a computer electrical engineer here at Oklahoma State, and I helped work on the AI part of the AI foosball team. Okay. So first, this is a continuing project, so this is our third semester on it. The first semester is this table behind me. This table runs a finite state machine, which means it is purely reactive. It only does what you program it to do. So this cannot get any smarter unless you completely recode it. So, to better improve our foosball game, we decided to implement an AI on our new table.
Why don't you show them some of the training processes that you use?
Absolutely. So, to begin with, an AI needs to learn how to play foosball. So that is done in this simulation. So we have about 128 tables running simultaneously at one given time. So as you can see here, this foosball is learning how to play. It's using deep reinforcement learning, which means all of its actions are given rewards and penalties. It is rewarded for doing a good action, like touching the ball and kicking it forward, and penalties for doing a bad action, like kicking it backwards towards its own goal, or taking a long time to score the goal. So once it's been fully trained, we can implement it over to the other table. The current brain on the table has been training for about 48 hours, so it's still pretty young, and it's learned how to kick the ball and score a little bit, but it is still very young and not that good.
Well, we'll show them. Over here we'll show an actual foosball game that they've got going. This is from the actual trained AI instead of rules-based play. Now the rules-based play in the past has beaten me multiple times. However, the AI, well, it's getting smarter all the time. So let's go look at the game they got going. Pardon me, big guy. Yeah. Okay, you want to talk about it, please?
So this is our foosball table that has an AI on it currently. So this AI, as I said before, has been training for about 48 hours, so it's still pretty young. The ball is tracked with this camera up top. That camera data is sent to the AI as well as raw positions. And that's sent to the AI. It computes the required raw position and then passes it back out to the table. So it's playing foosball as well as it can. So one of the main issues with our previous table is that it was large. It cannot be moved, and the actuation is on the side, making it very wide and loud. So this table, all the actuation is underneath the table. So we have the linear motion being controlled by little cable ties that move the rod back and forth. The rotation is controlled by a belt system. So the rods move back and forth with the cables, rotationally with the belt. And the main goal of this is to just kick it forward and try to get the ball as much time over here on this side of the table.
Now from AI foosball that we have, we're going to go over here and we are at a real BB-8 with true inertial drive. And what we can see here is that this is a demo of the initial drive, and in a minute we will have him show us the actual running BB-8.
Okay. Hello, we're BB-8. I'm Jared Campbell. I'm one of the electricals on this project, and this is BB-8. So right here we have a demo model of BB-8, and Trent, if you want to show the joystick to the people. So this is going to be controlled through a web-based interface, and the signal is going to be sent to our circuit over here, and that's how the controls work. Over here behind us we got the head, which can dispense cards. Dispense the cards.
Like you're out of cards.
Oh, are we? Yeah, it's not lined up.
Do you think you can get us another shot of it running?
Yeah. Give us a few minutes to set up, and then.
All right, so we're going to see the BB-8 run here. Now, while they're getting ready, I want to point out that what you're seeing is not just electrical engineers or mechanical engineers. These are a mixture of electrical engineers, mechanical engineers, engineering technology, as well as, sometimes we'll put in a chemical engineer. So once you start having all these type of individuals together with different disciplines, amazing things can be built. For instance, the AI foosball you've seen, all that has been only 3 semesters is all that's been put on this. And most of this was done in 2 semesters. So let's watch this roll here in a second when they get it fixed up. I'll run the facility.
Yes.
I mean, my goal is just to make sure most of my kids are not incarcerated, all right? Once they decide to be an engineer, all right.
Yes. First one was a chemical engineer.
Right.
Oh, yeah.
So what we're seeing now is it actually running with a true inertial drive. Are you controlling it?
Yep.
All right, let's watch it. All right. So pretty soon we'll have the head on top of it and do all the other things BB-8 does. But this is a big leap forward. I can brag, it's the only inertial drive robot that I know of in the world that's at a university. Yeah, I mean, think about it. This is it. Now, you're electrical or mechanical?
I'm a computer engineer.
Computer engineer. Excellent. That's kind of wild.
You good?
Oh, I'm good. It is. Last year, it cracked in 2. It's going to be a while before we can give proofs of it, Deborah. We'll be here next semester.
Groundwork has been laid.
That definitely. Thank you, gentlemen.
Thank you.
So now one thing that's a big deal in America and other places is the whole idea of building a tiny house. Well, one thing is building a tiny house, and then there's a bunch of engineers that build a tiny house. So obviously we want to have it off the grid, and we want to have it as efficient as possible. And that's what these students are doing here, a mixture of electrical and mechanical and all other kinds of engineers. So with me, I've got somebody to talk about the project. You can introduce yourself because I went, Jeremy, right?
Jared.
Jared, I was close. Please, Jared, take it away.
Okay. Well, yes, my name's Jared Youngblood. I'm a senior mechanical engineering, a part of the Zero Energy Tiny House team. And this semester we have just gotten our feet wet in terms of this multi-semester project, which will eventually result in a tiny house that is powered by solar panels and uses that energy to power a heat pump HVAC system. So the main goal with this is to demonstrate to potential students and anyone else that some of the engineering principles, they can be interesting. So our example for now is, say this tiny house could go out in front of Endeavor on a football game day. A lot of people can be walking through saying, hey, what's that? Come take a look, come figure out just a couple of things that engineers can do. So there's a future application where maybe something like this, if it becomes really efficient, can go commercial. But for now, the idea is that it just gets people interested in engineering.
So what are you doing with all these guys built here? What are you doing with these shells?
Yeah, so for the building team, which you asked the right man, because I'm the head of the building sub-team for this project, we wanted to know how thermally resistant a sample wall and roof could be. And that's these guys over here. So what we went ahead and did is constructed them with the idea that, yes, we can calculate these thermal resistances, but it's another thing to construct something not perfectly because it was constructed by 4 college students with no prior experience in construction, and to actually test those values. So to answer your question about these big old pink boxes, we use those to enclose 1/2 of the space, whether that be the wall or the roof. And within that space, we set up our space heater, which is just sitting on top of the roof there. It's a little space heater, so it's not going to burn everything down to the ground. We wouldn't like that. And we use this instrumentation, which includes thermocouples, which give us the surface temperature on one side, and heat flux sensors, which give us the surface temperature of the other side, along with the heat flux through the material. That gives us all the information that we need to go ahead and measure the R value of our wall and our roof.
Thank you. Thank you very much. And I've been watching them work on this now for a couple of months, at least, if not more. It's been a while. So they've been doing a very good job at that. Thank you very much, your whole team.
All right, I'm Jonathan Buskirk. I'm here with VMAX FSAE variable intake team here. So our goal of this main project is to take this Formula One car that a lot of OSU students made last year, and basically we're going to modify the intake system of that car. And basically all that we've changed is from here down to about where it connects to the engine here. But basically the premise of this project is to take advantage of what's called the Helmholtz effect. And so basically whenever the valve closes that allows air to enter the cylinder heads there, when the air bounces off that valve and bounces up, it causes a pressure wave to take place. And so we're trying to optimize the timing of that pressure wave so that when it hits the valve again, it's at full force, full velocity, coming into that cylinder head and hopefully broadening our torque curve. And so as you can see, the runners vary in length there based on RPM, and then with our results so far, we had about a 5% increase in our overall acceleration times. So that's the main gist of our project there, and we had some successful results. So
quickly, how the measurements that you've made on modifying the intake, how much improvement have you made?
yeah, so we made about we did our acceleration test, which is where the vehicle's from full stop to about 85 meters as fast as you can go, and we had about a 0.1 to 0.2 second increase in our time. So that's about a 5% increase overall, or decrease in time overall.
Okay, fantastic. So hopefully that'll translate into some more formula victories for Oklahoma State. Thank you, gentlemen. Much appreciated. So robots come in all shape and sizes, right? You can, from the autonomous vehicles driving to the inertial drive that you've seen. And from here, we're going to go from that to actually a one drive. And what these gentlemen are working on is basically locomotion as if you were an inchworm.
So we are Locomotors. I'm Brock Rouser, and we're working on the pneumatic soft robot project for this semester. Okay, yeah. So the motivation behind this project is STEM outreach in Oklahoma City and other summer camps across Oklahoma. We want to be able to demonstrate different mechanical and engineering principles to children K through 12. We plan to do this through our soft robot. Everything about this design is meant to be safe, hands-on, easy to transport, and cheap to manufacture. So the idea is potentially with a silicone body and nylon, a ripstop nylon as part of the driving force behind this thing moving, we can go underneath a door, we can have it move under or on top of various obstacles, and this is all accomplished through our pneumatic and electronic control circuits. Yeah, manufacturing was real fun for this one. All of this manufacturing is accomplished through pouring silicone into 3D printed molds. These molds are two parts that allow for us to develop actuators with air chambers and a kind of a fill line that allows us to expand and contract whenever there's an applied pressure. This is all done in the ATRC, where we use a vacuum chamber to degas our silicone to try and get all of the bubbles and imperfections out of it before we pour it into a mold, where we let it sit for about an hour or so, and it's ready to go. We just have to put a base on it, and and we can start moving it.
Well, thank you very much. Very cool locomotion, and the fact that you actually were able to 3D print and pour your own, I don't know, centipede, worm.
Yeah, whatever you want to call it. We're calling this the worm robot for right now.
Okay. It's quite wormy. Thank you. Kind of neat, isn't it? But a lot of projects we have, there's a lot of things in this world that's just obsolete that we keep holding on. But these young men have a solution that's actually going to be applied at Tinker? SimStar. So it already has a home based in industry with a definite need. So are you going to talk, or are you going to talk, or are you going to talk this time? Who's going to?
We can split it up.
That might be, okay, we're going to start here. Introduce yourself and start talking.
Okay, I'm Remington Ward. So SimStar gave us the task. Okay.
There you go.
So SimStar gave us the task. Oh yeah, you turned them on. Okay. SimStar gave us the task to turn the transmitter synchro to digital. So both of these are synchros, and as you can tell, as you turn it, there's a three phaser happening on the oscilloscope. So basically, what a synchro does is this will always go back to its position wherever the transmitter's at. So SimStar wanted us to make a digital thing, and right here, if you want to get a video of the PCB that Justin and Dylan made, we used digital synthesis chips and digital potentiometers to output the 3 stator signals and to be able to change them inside the SPI code. So you want to go next? Talk about the PCBs?
Okay, yeah, so we, after we picked out all the components we want to use, we put it all onto KeyCAD, which is a PCB designing software, made a schematic, and then we laid out and routed each trace on this board, sent it off to get it printed, and then we basically put all the components onto it with solder paste and use a reflow oven to bond them all to this PCB. And it all fits onto an Arduino Uno, which is our microcontroller for this project. I'll give it to you.
Okay, I'm Dylan. So I'll kind of just go over again what Remington was talking about, and then I can go over the software a little bit. So this is actually used in a lot of aircraft simulators in the industry. So the reason that these are used is because they're so reliable, and they can kind of, like you said, hold shape. So typically a dial will be placed on the transmitter side, and as you rotate the dial, it will rotate anything connected to it on the actual receiver side. So like obviously as we change it, it'll rotate, and it actually acts kind of like a transformer. So it's 3-phase power, and then we need to vary the amplitude of all of the sine waves to pretty high voltages. So it's about 11.6 VRMS, which ends up being about 32 volts. So our solution for that was to use digital potentiometers and, like you said, the digital synthesis chip. So we can generate a sine wave with the digital synthesis chip, and then we can vary the amplitude digitally with our software using the digital potentiometers. So if you want to, we can show you the software super quick. Okay, so this is our software. Kind of how we have this interfaced is you can enter the angle that you want on the transceiver side, and it will give us it'll rotate to show what the current angle should be, and then as you change it, it will actually change it on the receiver side, and it communicates with our device over in the Ethernet protocol. So as we adjust it, like he's doing now, it will change the digital potentiometers to change the voltage to get the correct signals. And so this can be directly integrated into SimStar's flight computer. And so the reason for doing all of this is traditionally the way to make things like this digital is using like a commercial digital device, which those typically cost like $5,000 to $6,000. So obviously for smaller companies and stuff, they can't really afford that, and it's not efficient. So what we've been trying to do is make this as cheap as possible. So in total, our entire device costs about $250 and uses our own custom software, as opposed to the $6,000 plus proprietary software. And so this can make everything more efficient for all the companies. And yeah, that's our project. Hi, I am William Randall. We are the Seat Parade Float team. Right here we have, how do you say your last name, Lewis? Louis Brio. Brittany Kelly. And Travis Thomas. So this here is Bertha. Actually, it's the parade float we built off of Bertha. You can see right here what we started with at the end of last semester was this machine. After we cut it down and refabbed it to fit in the trailer or the bed of the pickup. After that, we added on these beds so that way we have more foot space. The one in the front here, everything stays attached. It just folds completely over. But the one in the back over here, we'll see. We have plates made of plywood and diamond plate reinforced with 2x4. There's 3 of them. They pop off. We take out this orange bar here and the whole bed folds over onto itself. Everything stores nice and neat into the machine. We have cut out acrylic windows into the door so you can get a good look at the motors and the electronics. You can see our train horns in there. Not to mention, on the back here, we also have a window that shows off all of the electronics that came on the machine from the factory. Adjust your gaze up a little bit. That is the factory control panel that tells us about the machine itself, the power switch, the e-stops. Over to the left of it, we have the switch panel we installed, which controls the radio, the LED strip lights, as well as the lights on top of the machine, which we repurposed from the old systems. That's pretty much everything for the big machine. Right here next to us we have the small unit, which we were using to prototype the code that will eventually replace the software on the big parade float. We were using this to prototype the code that will run it to do the tricks, the crab walks, the 180 degree, the 360 about its center axis. Okay, I think that's about it.
And that's a lot.
Yes. I felt like that wasn't very much.
That's a lot. This is actually going to be featured a lot in a lot of parades across Oklahoma for both STEM outreach, but also for outreach for OSU and for our College of Engineering. It's actually the first maiden parade will be in June 16th. So we will see this in action. Thank you very much.
Thank you, sir.
So, what you'll see is that in thermodynamics we have a bunch of cycles, and what is better than combustion in an internal combustion engine? So what we've built is, our team has built, is a internal combustion engine that you put a load on, a stress on. It's called an auto cycle. And here to describe it is Mr. Nick. Nick, introduce yourself and talk about the system.
Okay, yeah, so this is our project. So we had to make a dynamometer for this engine here. So the way we did it is we went with a hydraulic dynamometer. So essentially we're using the engine to turn a hydraulic gear pump. And using the control valve on the system, we can restrict the flow and create back pressure, which will in turn add a load to the engine. And we can measure the load with these sensors we got over here. So we have a pressure sensor in the head of the engine, and we can map out what the pressure does over time, and we can see the pressure at the 4 different states of the auto cycle, and it gives us a good look at how it behaves when it's under different loads. Yeah.
And at Upaya, you will be getting the first generation of this. This is the second generation that these gentlemen put together. So, again, alright. What better than a team that works with fire, that learns all sorts of things like, you know, how hard it is to light people.
Alrighty, so I'm Tyler Lane, and our team is Iron Phoenix. So essentially, what we are trying to do is replicating a footprint of a 737 commercial airliner at a 1/6 scale. So our reason behind why we are trying to replicate this is to introduce a geometrical interference of a plane, so our sister project, the autonomous firefighting vehicle, can be able to fight a fire around a plane. So essentially, we're trying to replicate a case study of a real-world fire of Air China 120, where there was a fire due to a ruptured fuel tank. So as best we can to a 1/6 scale, we've tried to replicate the geometry of that case. So we learned a lot. So essentially, we learned that fire is very unpredictable and very hard to model mathematically, and that steel is really heavy. So
I was looking at that. I do not want to move that out. So hopefully before you guys leave, you bring a forklift or something, and I don't have to worry about it. Thank you, gentlemen.
thank you.
Now, we have a lot of good stories about autonomous vehicles, and here we're going to talk about 2 autonomous vehicles. One of them is for competition, and the other is for firefighting that we just talked about before.
So I'm Josh. I'm sort of the software and electrical engineer for the team. And this right here is an autonomous firefighting vehicle. Essentially, its main goals is to be able to put out an airplane fire on, so like at an airport, if someone crashes or messes up, completely autonomously without any human intervention. And it does this first by reading data from an IR camera, and to be able to see the fire, the heat signature of the fire itself, and detecting sort of a plume and distance to the fire, which it can send to a nozzle turret, which will be able to actually target the fire and put it out with fire suppressant. And the goal is for this whole chassis to be able to move completely autonomously to the fire. Or in other words, somebody in the tower could just hit a button, say, hey, go to this location on the tarmac, and the vehicle itself will launch from where it is, automatically plan a path to the fire itself, follow it, and then arrive at the fire to put it out. So right now, a lot of the work we did this semester was putting in an more advanced drivetrain than we started, because in the beginning we had a single axle in the back and it turned absolutely horribly. But now we split the axle, so we have a really good turning radius, put in extremely powerful motors, so we can go extremely fast, to sort of tune in the mechanical side of this. We also built up our own little electrical system to control the motors, or the stepper motors on our turrets, and then the algorithm itself that actually does all the targeting is completely custom, all made this semester. And we've been able to test it, spraying, targeting a fire, and driving, and we're actually going to do a drag race soon with it, so.
Now, are you going to be are you featured in Speed Fest this year as well?
Yes. Yeah, we're featured in Speed Fest. We're going to put out a fire and then drag race a jet car.
Ooh, that's going to be a lot of fun.
Yeah.
Well, thank you very much.
Thank you.
All right, from the autonomous firefighters to our competition team. This team also features, like most every team, both mechanical, electrical, computer engineering, and engineering technology.
My name's Brendan Wickman. I'm a EET. The main purpose of this project is to compete at IGVC, which is the yearly competition in Michigan. And so we're planning on making a fully autonomous vehicle. What that entails is adding a sensor suite of a few different cameras for lane tracking, object avoidance, pothole detection. We'll also have 3D LiDAR mounted in the grille, and then we currently have a planar LiDAR mounted at the bottom in the front and the rear. Again, for object avoidance and detection. Inside of the vehicle, we have our custom drive-by-wire system to control the vehicle remotely, and as long as a onboard computer that runs ROS that integrates with all the sensors and the drive-by-wire system over CAN to actually control the vehicle. And it's all interfaced with the GUI that we have built in to the dash to make it clean and a professional look.
Also that we've had is you've seen a lot of energy projects and a lot of projects involving efficiency. And this is one of the most innovative ones. Actually, I was a doubter until I saw their data. It's amazing what these guys are doing. So if you would, please introduce yourself and what your project is.
Yeah, so I'm Mason. I'm the project lead on thermal solutions, and we're working on a thermal energy storage tank. And what this is storing thermal energy in water inside the tank and using that thermal energy at a later time to either heat or cool a space. And the way we maximize the energy that we can get out of a system like this is by keeping our hot temperatures at the top of the tank and our cold temperatures at the bottom of the tank separate. The higher that temperature difference, the more energy we have. We can do this through the use of diffusers, which we have in the tank right now, through baffles, which you can see over here, which normalize flow, prevent mixing of temperatures, and allow, as we're flowing and cycling water through this and pulling heat out to use to heat a space, the cold water coming back isn't mixing and bringing down the temperature of the whole tank. We're finding about a 60% round trip efficiency, meaning we're using 60% of the energy that we put into this system, and that's rough estimates right now, very minimum. We're actually able to get more than that as we get more accurate in our data collection.
So I want to make sure I understand this correctly. So you have hot water being pulled from here going in to whatever system, and it returns back here as cold water, and these baffles slow down the diffusion so you actually can keep the cold water here, the hot water here, and there's a separation between the two.
Absolutely, absolutely.
That is fantastic. Thank you very much. One of the best teams that we've had is Cyclone Cowboys, and in this is where we try to develop the generators, wind generators, and try to improve efficiency. It's actually a Department of Energy test that we have, or a project that we're involved in. It's a competition, isn't it?
Yep.
Okay, so in this competition, we're using a wind tunnel in Endeavor that we normally use for normal courses, but it does double duty to where they can put in and optimize a design. But with me, we have, what's your name, son?
Sahir Vrani. I'm the team lead for Cyclone Cowboys.
Go ahead, please.
So, Cyclone Cowboys is a team based on the collegiate wind competition. It's a 3-part competition that is, so we have, of course, turbine design and testing that we see in the wind tunnel. We also have outreach, which is our, basically, they focus on growing the team, going out to schools to teach kids about renewable energy. They do interviews with industry experts. They do a lot of that kind of stuff. Oh, and social media. And then over there, you see our poster for project development. And what their purpose is that they create a hypothetical wind farm off of the Gulf of Mexico. They do all the calculations. They do like calculations for choosing a lease block, buying wind turbines, how much power they're generating, the cost for all that, including transmission stations, basically everything that you would need to build an actual wind farm. So it's a pretty big project, but luckily we have a pretty big team. We have about 30 people. That includes 18 capstone across 6 disciplines. Then we have some underclassmen helping out in various aspects of the project.
How do you feel about the recognition you guys got tonight?
Oh, it feels pretty great. We've been working on this for actually a year. This is a 2-semester project. Some of us have been carried over from last semester through an independent study program, but most of us are here for their capstone design. So it feels great to have that recognition.
What universities would you be competing against?
Oh, so we were selected. So there was a pool of 30 universities. 13 of us were selected. Oh boy, I don't remember all of them, but
that's okay. So basically, you made the cut.
Yeah.
Many teams down to the final 13.
Yep.
And we're going to win it, without a doubt.
Well, we'll see. I hope so. That's the plan.
I have no doubt. So thank you very much.
Thank you.
And don't tear up my wind tunnel, please.
Oh wait. Well,
I can't promise.
If it gets torn up, we'll make sure that you don't know about it. We'll fix it. We'll fix it all up.
All right. Congratulations, guys. Okay, as part of the tiny house, we worry about things like the HVAC systems, which is basically the heating and cooling system. So here, I got to see these guys do most everything on this. It's pretty interesting. Here we have
Wade Lopp.
Wade, go ahead and talk about your system.
So this is a heat pump and HVAC system that starts with this outdoor heat pump and takes a refrigerant into a heat exchanger that exchanges it to water. So then the water can go into this thermal tank, this thermal energy storage tank, and it can go into this unit which heats and cools your house. So what's really unique about this design is the thermal energy storage tank. The concept here is when you have excess energy in the daytime, since it's a zero energy home, you have excess energy when you have solar panels that are getting sun. You'd use that excess energy to heat up your tank. So then when you don't have any sunshine, you can use the hot water to pump through your system and you can still get heating for really cheap, right? It barely takes any power to pump things. What takes a lot of power is heating stuff up. So that's what we're looking at here.
Well, fantastic. And again, the goal is to build a tiny house that could be completely off the grid and very energy efficient.
Yeah, that's right. And minimize battery usage. That you don't want to have 20 batteries to have an off-grid house. You want to have like 2.
No, the batteries are expensive. So thank you very much, Wade, and congratulations on second. Fantastic. That's great.
Yeah.
Well, thank you.
Thank you.
So as you can see, we have a very dynamic senior design with hands-on. If you come to Oklahoma State, you can see the type of things that you'll be building and what you'll be experiencing when you come here. So when you start looking for universities or you start looking for a place to go to learn more, please consider Oklahoma State. I would love to see you in Endeavor. Thank you.